All right, so if you'll recall, yesterday we've got to the point where we can sort of start to do these grams to moles, use a mole ratio from the balanced chemical equation, and then we can go back to grams. Okay, that's our standard, that's our starting point for doing conversions, mass to mass conversions. Key is that mole ratio from the balanced chemical equation. Okay, one of the things that we want to be able to do, however, is we want to be able to deal with a situation where, let's say I mix two different reactants. Say I mix ethanol and oxygen and I burn them. Okay, I react my two reactants together. The question we want to be able to answer is what will happen? How much product will be formed if I mix two different reactants together? Okay, so that's one of the big questions we want to be able to answer, is how much will we get if we mix two different reactants together. We want to figure out which one of these will we run out of first, because it's likely that we would run out of one of these two first. We call the one we run out of the limiting reactant. Okay, and it's just doing a little bit of extra stoichiometry calculations. There's nothing special about it. We're just going to do an extra stoichiometry calculation. What we need to do is we need to be able to find the limiting reactant. Okay? So before we jump into doing this with mass and stuff like that, I'd like to spend just a sec and let's think about how we would think about this in individual molecules, sometime a little easier to hold in our heads. So we have our same reaction, our basic reaction of the ethanol reacting with oxygen to produce carbon dioxide and water. And let's say we went ahead and mixed 5 molecules of ethanol. 5 molecules of ethanol and 12 oxygens. So I have a little tiny reaction vessel and I put 5 molecules of ethanol and 12 molecules of oxygen. Okay? Now, what's going to happen is one of the ethanol molecules is going to combine with 3 of the oxygens to produce 2 carbon dioxides and 3 waters. So we used up one of the ethanols, and when we used up one ethanol, that takes 3 oxygens. Then we can have a second ethanol react with another 3 oxygens. Okay? And then we'll have a third ethanol react. And finally, a 4th ethanol react. And at this point, the reaction stops. Why does the reaction stop? We ran out of oxygen. So in this, what is my limiting reactant? Oxygen was the limiting reactant. If I wanted to do any calculations based on how much products were formed, I'd have to base those calculations off of the oxygen. Because I have excess ethanol. If I did calculations and started with 5 ethanol molecules and said, oh, I have 5 ethanol molecules, that means I can produce 10 carbon dioxides. Could I really produce 10 in this situation? Nope, because I don't have enough oxygen to react with all 5. I had 12 oxygen molecules. Divide by 3 times 2 means that I should make 8 carbon dioxides, which is what I did make. Okay? So, again, first thing we have to figure out if we're given 2 reactants is which one is the limiting reactant? Which one will I run out of first? Because that's the one I need to base all my calculations off of. That's the one that I have to start with when I go through and do my stoichiometry problems. So it's fairly easy to see how we can, when you're looking at just individual numbers of molecules, you're going to take the coefficients here and figure out which one do I need. The general procedure is to pick one of the 2 reactants and calculate how much of the other one do you need. So if I had 5 ethanol molecules, how many oxygens would I need? 15. For every one of these, I need 3 oxygens. If I have 5, that would be 3 times 5, or 15. I only had 12, so oxygen was my limiting reactant. if I want to do calculations about how much will be produced, I better start with that 12 oxygens. So, of course, it's not really enough to just do a few molecules. We want to be able to do these same calculations with mass. Okay? So if we had the situation we've been talking about, 100 grams of ethanol, and we're reacting that with 100 grams of oxygen, okay? We want to figure out what's my limiting reactant. Pick one of the two reactants to start with. I'm going to pick ethanol. So I'm going to start with the grams of ethanol. So I'm going to start with my 100 grams of ethanol. I'm just kind of randomly picking. Sometimes you can develop a little intuition. Sometimes the one with a higher coefficient might be a better way to go. But since molar mass plays a part there too, you got to take that into account. So I picked my 100 grams of ethanol as the point to start. Now I'm going to do a stoichiometry calculation that says how much oxygen do I need to use up 100 grams of ethanol. So I'm starting with ethanol, and I'm calculating oxygen. We know how to do this. I'm going to convert from grams of ethanol into moles. Then I'm going to go ahead and convert from moles of ethanol into moles of oxygen. Where did I get this ratio, a 1 to 3 ratio? Balanced chemical equation, 1 ethanol to 3 oxygens. Now I'm going to go ahead and convert back from moles of oxygen into grams of oxygen. 1 to 32. And so I can go through and I can do this calculation, and to use up 100 grams of ethanol, I will need 208.4 grams of oxygen. That's how much oxygen I need to use up all of the ethanol. Do I have enough oxygen? Nope, I only have 100 grams. So which of these two reactants will I run out of first? Yep, I have not enough oxygen. That means I'm going to run out of the oxygen first. That means oxygen is my limiting reactant. So if I want to calculate how much water can be produced, I need to start with the limiting reactant. You use the limiting reactant as the starting point in stoichiometry calculations. I'm going to start with my 100 grams of oxygen. That's the limiting reactant. I'm going to do my standard stoichiometry problem. Convert the grams into moles. Okay, I'm converting from 100 grams to moles of oxygen. Now I know that it's a 3 to 3 ratio. Where does that come from? 3 oxygens to 3 waters. Okay? So now I can convert from moles to grams. And that will tell me that I can make 53.3 grams of water. 56.3, excuse me. 56.3 grams of water. So, there's one other question we're frequently asked. And that is, well, if oxygen is my limiting reactant, which means I use it all up, how much ethanol is left over? To calculate how much ethanol is left over, we need to find out how much ethanol do we use up. So what we want to do is a stoichiometry calculation that now starts with oxygen and calculates how much ethanol do we use up. Same stoichiometry, same setup. Start with your 100 grams of oxygen, convert from grams to moles. Use the ratio. In this case, it's 3 moles of oxygen to 1 mole of ethanol. Notice these things are canceling out, right? That's why I'm using this dimensional analysis to help me see that. And then I can convert back from moles of ethanol into grams. And I can find out that we would actually need 47.99 grams of ethanol. That's how much ethanol we need to use up to burn, to react with all of the oxygen. That would use up all the oxygen. So I take how much I started with minus how much I used up, to get how much is left over. If I mixed 100 grams of ethanol and 100 grams of water or oxygen and reacted them, set them on fire, I would have 52.01 grams of ethanol left at the end of the reaction. There would not be enough oxygen to use it all up. Okay? So limiting reactant problems are just expansions on stoichiometry problems where you have to figure out which one of the things do you run out of first. That's all you have to do. You have to figure out which one do you run out of first, which one is the limiting reactant. Then base your calculations on that limiting reactant. Okay? Question? 47.99 grams, that's the grams of ethanol we need to use up all of the oxygen. I started with oxygen and I calculated how much ethanol would I need. All right? All right, your turn. What if you did the galactose? 100 grams of galactose reacting with 100 grams of oxygen. How much water would be made? How much water would be made? And how much of what reactant will be left over? How much water would be made and how much of what reactant will be left over? All right. All right.
I just want to point out that galactose is almost exactly 10 times as heavy as water.
Wow.
Like almost exactly.
Crazy. All right, so our first calculation, let's say we started with oxygen. Right? My first step is to say, hey, if I use up all the oxygen, how much galactose do I need? Okay, so I start with my 100 grams of oxygen. I convert from grams to moles. I use the mole ratio. Okay, I use the mole ratio. 6 moles of oxygen to 1 mole of galactose. Remember, that comes from the balanced chemical equation. 6 to 1. Okay, 6 to 1. So that's my 6 to 1. Then I convert from moles of galactose back into grams, and I say, hey, look, to use up all of the oxygen, I need 93.83 grams of galactose. Do I have enough galactose? Yeah, I have more than enough galactose. So what will I run out of first? I will run out of oxygen first. Oxygen is, again, the limiting reactant. If you had started this calculation with the galactose, you would get an answer of that you need something like 106 grams of oxygen. And then you say to yourself, wait a minute, I don't have 106, I only have 100. I'm going to run out of oxygen first. And if I run out of oxygen first, oxygen's my limiting reactant. So the next step is to do that calculation and say, okay, that I'm going to start with oxygen and I'm going to calculate how much water I can make if I use up all the oxygen. These stoichiometry calculations are presuming that whatever you're starting with is going to get completely used up. That's why we can't start with the galactose, because the galactose isn't going to get completely used up. I'm going to have this left over in the container after I'm done. So, grams to moles, mole ratio, 6 oxygens to 6 waters, and then back from moles to grams. I find out that I will make 56.31 grams of water. Okay, 56.31 grams of water. Last question I want you to answer is, The last question is, how much galactose is left over? So, you need to get this number. If you picked oxygen to start with and calculate the galactose, you have it. If you picked galactose to start with and you got oxygen, you need to go back and do this calculation. Okay? So it's one of those things where it's like if you guess correctly and you start with your limiting reactant, you saved yourself a stoichiometry calculation. But if not, if you get, if you started with galactose and got 106 grams of oxygen, then you'd need to do a third equation, which would be this one, where you start with the oxygen to calculate how much galactose you used. This is the amount of galactose we used up. So we take the total 100 grams minus how much we used up to get how much is left over.
Why do you need that?
Because I asked you to find it. And generally the problems of this type will frequently ask you to calculate how much of one of the products will be made and how much of which reactant will be left over. That's a very typical question.
How much lenience, I got 0.08 grams off,
If you're off in this last digit, it's probably a rounding issue. Or you use slightly different values for the masses. And it's usually okay. Question? We're going to assume that these are actually 100.0. Yes, it would. You are correct. 6.2. Things to look for are things with high molar masses and high coefficients. Because then you have a small number of moles, or you need a lot more moles. So high molar masses and small coefficients. So, and then in this case it's tricky because this is a high molar mass and this has a high coefficient. And they're actually really, really close. Right? This is almost exactly how much we need. Now, if you have a mixture that comes out exactly right, we call that a stoichiometric mixture. Okay? Because it was just exactly the right amount of each reactant. That's particularly efficient in terms of you don't have anything left over, you used up all your reactants. All right? Now we have a big glass of water. Yay, us. That clock is not right. That's messing me up. What do we got, like just a couple of minutes left? 1 minute? All right, we're going to do this real quick, okay? So here's what we've got. We're reacting hydrogen with oxygen. Okay, we might go into a passing period for just a sec. That clock messed me up. I will write you a pass if it's necessary. So what are we reacting together? Hydrogen and oxygen, okay? So first, let's look at what happens if we have just oxygen. Okay, so just oxygen. So what happened with just oxygen? Not that much, okay? So let's take a sec and we'll do just hydrogen. So this is a hydrogen balloon. It has just hydrogen in it. Now this might be a little bit more vigorous. Oh, I don't have time for this. So here's our hydrogen. All right, not done. Hold on, give me a sec. Hold on a sec. All right, this is a 50-50 mixture. 50-50 mixture. 50% hydrogen, 50% oxygen. Okay, 50% hydrogen, 50% oxygen. Hey guys, can you wait outside for a few minutes? Can you keep kids outside for a sec? Thanks. Yeah, right there's fine. 50-50 mixture. Hold on, we got one more. So 50-50 mixture. Now, mixture now. Yeah, you can close it if you want. That's fine. Or you can open it either way. I don't care. Or you can open it all the way. I don't care. I'd close it. All right. So 50-50 mixture. This is a 2-to-1. Why is that be a special number if you think about this equation? 2-to-1 ratio. What's the ratio? Hold on, I'll write you a pass. It's okay. All right, if you need a pass, write it out. I'll sign it in the hallway. We'll talk about this third period.